So S and T are monoids. S and T are monoids. Okay. So we have two properties. The first property is x y of f is equal to x f y f for all x y belongs to S. Second property, the image of identity of S under F is equal to the identity of T. So these are two properties. It's called monoid morphism. The first one is called the semigroup morphism. The first one is called semigroup morphism. Semigroup morphism. And the second one is called the monoid morphism. Is called the monoid morphism. It's called the monoid morphism. These are two properties. The monoid morphism has two properties, and the semigroup morphism has only one property. Now we'll see that if we have two monoids and there is a semigroup morphism between these two monoids, then that morphism need not be a monoid morphism. That means that semigroup morphism need not preserve the identity. Okay. So as you know, in case of groups, we know that if f we know that if f is a group morphism, is a group morphism between the groups G and H, between the groups G and H, then f of 1 G is equal to 1H. That means this 1G is the identity of G and 1H is the identity of H. That we know, it preserves the identity. But it's not true in case of monoids. Now if S and T, okay, it's left side actually. Right. It's f of this 1G. So this you know between the groups है. अगर group के दरमियान कोई morphism होगी, that morphism will always preserve identity. That you know. Now if S and T are monoids and f from S to T be a semigroup morphism, not a monoid morphism, be a semigroup, morphism, that is okay. So next page, okay, be a semigroup morphism. That is semigroup morphism means it has only one property, okay, that is x y f is equal to xf yf. Then f need not be a monoid morphism. Monoid, that is 1s of f need not be equal to 1t, where 1s is the identity of s, where 1s is the identity of s and 1t is the identity of t. तो इन फ्यूचर हम ये जो है ना 1s और 1t ये नोटेशन हम इन फ्यूचर में यूज नहीं करेंगे, हम सिंपली लिखेंगे f of 1 equal to 1, where it is understood that this one is the identity of s and that one, the identity on the right hand side, is the identity of t, the codomain of the map. Okay, तो 1s और 1t हम यूज, इट्स अंडरस्टूड है, क्योंकि जब आप f of 1 निकालोगे ना 1s, it means that this 1s is the element of s, so we don't write s in future, we simply write f of 1, so that means 1 is the identity of s equal to 1, not 1t, we simply write equal to 1, and this one it is understood that it will be the identity of t. So we'll see that if we have a semigroup morphism between two monoids s and t, that means xyf equal to xf yf, then this semigroup morphism need not be a monoid morphism. That means it may not preserve the identity. आपके पास कोई एग्जाम्पल है? मैंने एक एग्जाम्पल तो कंस्ट्रक्ट की है मैंने इसकी, where we have two monoids and there is a morphism between these two monoids which is a semigroup morphism, but that morphism is not a monoid morphism. सबसे पहले हम देखें कि प्रॉब्लम कहाँ पर आ रही है एक्चुअली, तो उससे हमें थोड़ा आइडिया मिलेगा कि एग्जाम्पल हम कैसे कंस्ट्रक्ट करेंगे. ओके, ठीक है. सो let's see in case of groups, why this f of identity is equal to the identity, why it's true in case of groups, why this is true. Okay, why the identity of E is equal, the image of E is E, where this is the identity of domain and this one is the identity of codomain, is true in groups, is true in groups. The answer is simple, because we have this f of E, f of E is equal to E. Okay, let's write it as because this is true, it's equal to EF. So this means the image of E under F is equal to E. Okay. Because here it means that E into EF. Okay. So this E is the identity of the codomain. So we are actually applying the cancellative law. We are applying the cancellative law here actually, and it's because we are cancelling these two, f of E and f of E, and we get E is equal to EF. As E into EF is the identity, so E into EF is equal to EF. Okay, so this is EF, it's equal to E into EF, EF. And on this side, since f is a morphism, it's EF. So we can cancel out these two, EF and EF, and we get EF is equal to E. So you must take, if you want to construct an example, then you must take the semigroup T to not be a cancellative semigroup. where this cancellation is not possible, because whenever this cancellation is possible, we always have the preservation of identity, because we are only applying the cancellative property actually here, not the inverse property. Yeah? We are only applying the cancellative property, and groups hold this cancellative property. So is there any semigroup where this cancellative property doesn't hold? Yes? And cancellative property actually hold through inverses, you can say, because we are applying the inverse throughout. Set of natural numbers. इसको erase करें. No. Set of matrices. Yes, exactly. Set of matrices is a good example of it. So let's take this T. Let's take T equal to set of all. Say let's take 2 cross 2 matrices, because we have to take the semigroup where the operation is multiplication, so we must take the square matrices A, B, C, D, where these A, B, C and D, they are just real numbers. And this one, it's a semigroup with respect to multiplication. It's not a group, and in this semigroup we don't have multiplication property, because okay, let's take S equal to this one. S equal to set of natural numbers. Okay, then S and T are semigroups, or with respect to the usual multiplication in N, and the matrix multiplication and the matrix multiplication in T. Okay, they are both semigroups. In fact, they are actually monides. So we can say they are both monides, not only semigroups, they are monides. With identities. What's the identity of S? Its set of natural numbers under multiplication, its identity is 1. Okay? And what's the identity of this T, the 2 plus 2 matrices? It's just this one, 1 0 0 1, respectively. Okay? आपने इसको नोट किया? Okay. Now we want to define a function between S and T, which is a semigroup morphism but not a monad morphism. Define F from S to T. Okay, that must erase this. Define F between the semigroups S and T, where S is a set of natural numbers, T is the set of matrices. So any idea how to define this? By n of f is equal to, तो यहाँ पर 2 क्रॉस 2 मैट्रिक्स होनी चाहिए. मैं चाहता हूँ कि आप ये खुद डिफाइन करो, और इसका ख्याल है कि दिस मैप शुड नॉट प्रिजर्व आइडेंटिटी. It should be morphism but not should preserve identity. It should be semigroup morphism. Yes. हाँ?
सर हम कुछ भी डिफाइन कर सकते हैं.
कुछ भी डिफाइन कर सकते हैं, बट इट शुड बी मॉर्फिज्म, सेमी ग्रुप मॉर्फिज्म, which will not preserve the identity.
आइडेंटिटी के लिए सर अगर हम पहले में लेंगे n.
Yes.
The second one sir.
One may create problem. It may not preserve the multiplication operation here. If I define like this, f of n equal to n, yes, 0, 0, यहाँ पर क्या रखूँ?
n plus something अगर रखेंगे,
n plus something, वो भी प्रॉब्लम करेगा क्रिएट मल्टीप्लिकेशन में, बिकॉज इट शुड प्रिजर्व मल्टीप्लिकेशन ऑपरेशन. आप और भी देख सकते हो, 2n में ले सकता हूँ शायद. हाँ यस, 2n विल आल्सो वर्क, मगर यहाँ पर आपको ख्याल रखना चाहिए 0 0 0 मैंने लिया ना, यू हैव टू चूज दोज एलिमेंट्स. Then you can see this, then nm of f, it's equal to n m 0 0 0, that's equal to n 0 0 0 and m 0 0 0. और अगर आप यहाँ पर 1 लेते ना, n then 1, अगर यहाँ पर 1 2, वहाँ पर प्रॉब्लम हो सकती थी, वहाँ पर शायद आप इसको ऐसे एक्सप्रेस नहीं कर पाओगे. फिर दिस इज इक्वल टू एन एफ एम एफ. हाँ, अगर आप लेगो n, अगर आप इससे लोगे ना, दिस इज n 0 0 n, मगर यहाँ पर भी n लोगे, डायगोनल एंट्री में n लोगे, वो भी मॉर्फिज्म होगी, बट दैट विल प्रिजर्व आइडेंटिटी, क्योंकि उस केस में f of 1 क्या आ जाएगा, 0 1 1 1 1 0 0 आ जाएगा, डायगोनल एंट्रीज 1 1 आ जाएगी. क्योंकि अगर दोनों डायगोनल एंट्रीज आप n लोगे ना, n, ये मॉर्फिज्म तो रहेगी, मॉर्फिज्म रहेगी, मगर ये फिर उस केस में आइडेंटिटी को भी प्रिजर्व करेगी, क्योंकि उस केस में 1 की इमेज क्या आ जाएगी, 1 1 फर्स्ट एंट्री 1 0 0 1, मतलब ये आइडेंटिटी मैट्रिक्स बन जाएगी. तो इमेज ऑफ आइडेंटिटी है, मगर हमें क्या चाहिए, इमेज ऑफ आइडेंटिटी शुड नॉट बी इक्वल टू द आइडेंटिटी. तो उसके लिए ये एग्जांपल सही है, इट्स अ सेमी ग्रुप मॉर्फिज्म. सो therefore f is a semi group morphism, but the image of 1 under f is equal to 1 0 0 0, which is not the identity, which is not equal to 1 0 0 1. Therefore f is not a monad, f is not a monad morphism, f is not a monad morphism. So semigroup morphism need not be a monad morphism. Now we define isomorphism. 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 a morphism F between the semigroups S and T, is called an isomorphism. Is called an isomorphism. If it is invertible. If it is invertible. So invertible का मतलब क्या है? There should exist F inverse between the semigroups T and S such that the composition F inverse is equal to identity on S and F inverse F is equal to identity on T. Okay, that is, मैं next page पर आ जाऊँ?
Yes, sir.
That is there exists a morphism F inverse between the semigroups T and S such that there exists a morphism F inverse between the semigroups T and S such that F inverse, which is a function from S to S, because F is a map from S to T, F inverse is a map from T to S. First one जो है ना, it's a map from S to T. Second is from T to S. So composition will be from S to S. S to not S to T, S to S. So that F inverse, it's a map from S, is identity. It should be identity on S. And the second composition F inverse F, it is a map between the semigroups T and T. This should be an identity on T. So there is an exercise for you. Show that a morphism, it's very simple, morphism 5 between the semigroups S and T is an isomorphism. If and only if phi is bijective. If and only phi is bijective. ये आपके लिए असाइनमेंट भी है, साथ साथ जो भी एक्सरसाइज होगी ना वो असाइनमेंट है. Then if phi from S to T is an isomorphism, then we see S and T are isomorphic. isomorphic, and we write this S is isomorphic to T. Now if isomorphism on S means it's a morphism from S to S, then we call it endomorphism. If phi from S to S is a morphism, then we call it an endomorphism. And if phi between the semigroup S and S is an isomorphism, then we call it an automorphism. Same as in case of groups we have created. Automorphism and endomorphism. Next, we define the Cartesian product of two semigroups. Then we try to generalize this product of two semigroups to any arbitrary family, for the product of any arbitrary family of semigroups. Direct product of semigroups. Let S and T be semigroups. Then their Cartesian product S cross T, which is the set of ordered pairs, then their Cartesian product, then their Cartesian product S cross T, which is equal to this set ST, such that S belongs to S and T belongs to T, is a semigroup. Is a semigroup.
लेट से आ रहा है जो आप लिख रहे हैं.
लेट आ रहा है. So एक्चुअली मुझे वो पेज इरेज करना पड़ा क्योंकि इसमें लैपटॉप में थोड़ी प्रॉब्लम है, तो उससे भी शायद प्रॉब्लम होती होगी आपको. मैंने वो पेज ना इरेज किया. Then their Cartesian product S cross T, which is equal to the set of ordered pairs ST with S is in S, T is in T, is a semigroup where the multiplication is defined by is component wise. Is point wise or component wise, you can see. Component wise, that is S1 T1 and S2 T2, it's equal to the ordered pair S1 T1 S2 T2 for all S1 T1 S2 T2 belongs to S cross T. Okay.
S1 T1 हो गया, S1 S2 T1 T2।
एक ही बात है। आप S1 T1 फर्स्ट एलिमेंट S1 में है, सेकंड एलिमेंट फर्स्ट एलिमेंट S का है, सेकंड T का है, इसलिए